This was an example that I just came across earlier in the month. Really nice idea. Basically what somebody did was they looked at all of the sets of Lego that Lego have ever manufactured. And in this case, instead of documents and words, you've got Lego sets and bricks of different colors. And they basically apply topic modeling to identify these kind of emergent color schemes that you see in Lego sets across the last few decades. It's a really nice application, and I want to try the data set. But it just shows you can do a lot of other things with topic modeling. But today I'm going to focus on text. I'll try to go through some of the fundamentals of working with text data, which you need to understand before you get into looking at topic modeling. Generally speaking, when you're talking about text data, you're talking about unstructured data. So you're talking about data that isn't marked up, it's just natural language. And obviously the form of that language can vary significantly. So maybe we have something like really nice structured news articles. Maybe we have something like, I don't know, literary text, but it's been scanned, so there are OCR errors in it. And then maybe you have things that are not really quite as nice. Apparently Twitter thinks this tweet here on the left is Indonesian. It could be this on the right here. Again, not going to be great from the point of view of topic modeling, but there's still a signal here of sorts. So when you've got your piece of unstructured text, typically the first thing you're going to do is tokenize that text. So in other words, take your text and split it up into individual words. For English, this is pretty straightforward. You might use white space. You might also take into account obviously other characters. You get a string like this and split it into the individual tokens, as we call them, that make up that sentence. Now obviously, for other languages, Chinese, Japanese, Korean, even German, this is a bit more problematic, but there are Python libraries out there, libraries in other languages, that can deal with these languages well as well. One thing just to bear in mind is that if you're dealing with text where characters have special significance, so tweets, obviously the hashtags, mentions, so on, you just need to be a bit careful about how you split up your text. You don't ignore the hash symbol, because obviously it has a special significance in Twitter data. So the question then is, how do you go from these tokens in your text to some kind of numeric representation that your machine learning algorithm can work with? And probably quite a few of you have come across the idea of the bag of words model. So this is the kind of the standard approach for numerically representing text. So basically each document is represented by a vector. That vector has m dimensions, and m corresponds to the number of unique terms or words in your corpus vocabulary. So imagine we have these three documents here. When we tokenize them and we split them up into their individual words, we've got 14 distinct terms here. So there are 14 terms in the vocabulary of these documents. So what we might do then is build this vector space. So you see the columns there correspond to each of the terms in the corpus vocabulary, and then the numbers correspond to the number of times each of those terms has occurred in that particular document. So now we've got this numeric vector that represents this document. We can do the same thing for our three other documents. We can stack those vectors together, and suddenly we have this matrix now. This is what we call a document term matrix. We've got 3 rows for 3 documents, and 14 terms. This is the corpus vocabulary. And a lot of techniques in machine learning, text classification, whatever it might be, work with this type of representation. It's naive in the sense that you've lost the kind of the sequence in the text, but typically you can still do a lot of useful things with this type of representation. So going back to scikit-learn, scikit-learn makes it very easy to build these types of bag of words models on text data. Let's say you have a list of strings. So these are this list is your list of documents. This can vectorize a class. If you apply this fit transform function, basically will take all of those strings, which are your documents, tokenize them, build this vector space model, and create this matrix A. One nice thing is that A is a sparse NumPy two-dimensional array, where the rows correspond to documents, obviously, and the columns are terms. The reason why it's important that it's sparse is that in this type of vector space model, or this bag of words model, generally speaking, most words won't occur in most documents. So typically you'll end up with maybe 98, 99% on average 0 values in your matrix. So if you don't represent it as a dense matrix, you want to represent it as a sparse matrix, uses far less memory. It means that on your laptop you can easily process hundreds of thousands of documents potentially. Once the matrix has been created, you can access the vocabulary, either getting just a list of the terms or getting a dictionary where you can index in to find out what column in your matrix corresponds to a given term. There's a lot of things you can do just beyond simply counting the number of words that occur in a given document, and there are things that you might do to kind of reduce the number of words that you include. You might exclude terms that are less than a certain length. An obvious thing to do is convert everything to the same case. Something that's the importance is kind of underestimated of is the idea of a stop word list. So just common words that you want to exclude because they don't have any particular meaning, or because in your particular type of data they occur in practically every document. You can also kind of do a sort of more automatic approach where you either filter terms that appear in very few documents or in a very large number of documents as well. And finally, you can do things like stemming, where you try and remove word endings, plurals, ing, and so on, to kind of regularize or normalize your vocabulary. Scikit-learn can do most of these things very easily. Again, you use this count vectorizer to kind of activate these pre-processing steps. You just set the various parameters that you pass into the count vectorizer class. So for example, if you specify the stop words parameter, you can pass in a list there of custom stop words. Min-df is the minimum number of documents in which a term has to appear for it to be included. Similarly, you can have a max-df. Lowercase actually is normally true by default, so everything gets converted to lowercase. I won't kind of talk about it too much here, but there's also this n-gram range parameter as well. And what this means is that an n-gram is a phrase of length n, so a bigram has 2 tokens in it, a trigram has 3 successive tokens in it, and so on. So it allows you to not just use single words, but if you want to incorporate phrases as well. So not just include the token Trump as a term, but include the 2 tokens Donald Trump successively as a term in your model. One other important aspect when it comes to working with text data is the fact that not all terms are equally useful in your model. So as well as just excluding certain terms, you can also potentially improve the usefulness of your document term matrix by giving higher weights to certain terms. And this is where the idea of TF-IDF comes in. It's a weighting scheme for terms. It's quite widely used in classification, in information retrieval, and so on. And the idea is that it consists of 2 parts. The term frequency is just some function of the number of times that a term occurs in a document. And then the inverse document frequency is some function of the total number of distinct documents that contain that term. And I won't kind of belabor the formula too much, but the idea is that you're kind of penalizing terms that occur in a very large number of documents, but occur less frequently in one specific document. So to give you an idea of what that looks like, imagine you have the term cat, and it appears in this specific document 3 times, but it appears 50 times overall in the inner corpus of 1,000 documents. Effectively, what TF-IDF does is it reweights, it transforms that value 3 into this value 11.987, and if you had another term, let's say dog, and it appears 3 times in a document, but it appears 200 times overall in our corpus, it'll get a lower weight. So you're kind of downweighting the things that are very frequent, upweighting the things that are less frequent. And this often gives you a better representation of your data. This can be applied very easily again in scikit-learn. The only change from what I showed previously is that count vectorizer gets changed to TF-IDF vectorizer. After that, then it's applied in the exact same way. You apply fit transform, gives you back a document term matrix. You can pass in parameters to it if you want to apply pre-processing steps and so on. So it's very easy to, all of this sort of complexity in terms of the weighting scheme and so on is hidden from you in scikit-learn, but of course it's useful to know what it's doing. So just to kind of finish up the idea of text preparation, a text processing pipeline looks a bit like this. You start off with your corpus of raw documents. You're definitely going to apply some kind of tokenization step, and then these steps in blue, case conversion, filtering short term, stop word removal, min-max term filtering, stemming, and so on. You might apply those. They're optional, but they're often useful. Then you'll have this vectorization step, which you'll always apply, which gives you your ultimate matrix. You could, before you kind of do your whatever the analysis you're going to do, apply term weighting at that point. One minor point is that stemming is not included in scikit-learn. If you want to do that, you need something like the NOTK package. So now we have a document term matrix representation. So we've gone from our original large collection of text documents to this large sparse matrix that we'd like to kind of discover what's in that matrix. What are the patterns that are in that matrix? And this is where topic modeling comes in. There's two general approaches to topic modeling that are quite widely used in the literature. The one that's probably most common, and when you mention topic modeling to people, particularly if they're from a statistical background, they'll think of approaches like latent Dirichlet allocation, which are they're effectively probabilistic approaches. The idea is that you view each document as some kind of mixture of topics, and then you try and figure out what the probability of each word is and each document is for a specific topic. And these are quite popular techniques. The techniques that I'm going to talk about now are an alternative. They're based on the idea of matrix factorization. And what this means is you're taking methods from linear algebra, and you're taking your large matrix, your document term matrix in this case, and decomposing it into smaller matrices that we can interpret more easily. And the sort of the canonical example of this, which I'll talk about, is non-negative matrix factorization, or NMF, which was popularized in 1999. An interesting thing about NMF is that it was initially applied for things like image processing and in bioinformatics. It's been less widely applied for analyzing text data, but it's also very good for that as well. So, like I said, NMF can be applied for topic modeling, and typically what you do is you apply it to your TF-IDF normalized matrix, so the one that we created as I showed earlier. The input is this matrix, and also you specify the number of topics, K. And that's a common thing that you see in any of the standard topic modeling algorithms, whether it's NMF or LDA. It's kind of equivalent to specifying the K in K-means if you're familiar with clustering. So we start with our matrix A, which has N documents and M terms. And the idea is that NMF basically decomposes that into two much smaller matrices, which we call factors. W now has N rows and K columns, so N is the number of documents, K is the number of topics, and then H has K rows and M columns, where M is the number of terms. And basically what this does is it gives us a relationship between documents and topics, that's the W, and topics and terms, that's the H. And obviously the columns in W and the rows in H correspond. So topic 1 in W corresponds to topic 1 in H, and so on. It's probably easiest to understand if you see a very simple example. So imagine we had a term document matrix like this. We have 6 documents and we have 10 terms. The light squares just indicate zeros, and the darker squares indicate larger numbers. What NMF does, if it's applied to that matrix, is it gives you these two factors, W and H. And what we see in W here is that for the first topic, documents 3 and 4 are reasonably strongly associated with that particular topic. For topic 2, we see that document 1 and document 6 are strongly related with that particular topic. And finally, for topic 3, we see that document 2 and document 5 are strongly related. Now, as I said earlier, in some cases you might have documents that are related to multiple topics, but in this case, the simple toy example, they aren't. Now, the useful thing is then you can say, well, okay, we know that these documents are related to these topics, but what are the actual topics? What do they mean? if we look at the relations between the topics and words, we see that maybe the first topic is related to things like finance and banking, the second one is related to, I guess, health, and the third one is related to education in some way. So NMF is giving us this association between documents and topics, and then also terms and topics as well. Scikit-learn includes a very fast implementation of NMF. The implementation was kind of rewritten from scratch about 18 months ago, and it's really efficient. You know, scalability and performance is one of the prime benefits of NMF, one of the reasons you might choose it over LDA. One thing to note is that by default, this kind of factorization process where you produce the WH involves choosing a sort of set of random initial values for those factors. So you're making a sort of a random guess at the start as to what your topics might be. And that's important, I'll talk about that in a minute. The only key required input parameter for scikit-learn when you call this decomposition.nmf is the number of topics, or the number of components, so how many topics you want to choose. You apply, again, the fit transform function that is common in scikit-learn. That gives you your W, and you can also then access the H. So, typically for the sample data set that I've included for the notebook has about 5,000 documents. It'll take less than a second to give you your results back. If you were talking about 50,000 documents, you might be talking about 4 or 5 seconds. So it's a fast process. As I said, random initialization. What happens is that potentially you can get different results on the same data when you run it with different random seeds. This is actually the same case with LDA as well. So without going into too much detail, you can also use SVD, singular value decomposition, to initialize NMF. It gives you more robust results. And this parameter here, init, when you're calling decomposition.nmf, allows you to use that type of initialization, and it does tend to give better results. So the output are these W and H matrices, as I said. If you look at the H factor, it gives you term weights relative to the K different topics. You can sort the terms for each topic, and they give you the descriptor that I talked about at the start. So if you remember, I showed the tag clouds that represent the top terms for a given topic. When you're applying this in Python, what you're going to do is you're going to look at the weights for each topic, sort those weights, and then find out what are the terms that correspond to those particular weights. So for this set of news articles that I mentioned, you might get something that looks a bit like this. If you set K to be 8, you get a set of 8 topics, and then a ranked list of the top terms for each of those topics. Here I'm just looking at the top 10 terms. And you can get a sense immediately of what these topics might be about. The first one potentially relates to Brexit. The second one, Trump-Clinton presidential election, films, football, banking, health, music, and then I guess the last one is kind of internet technology and so on. So you're getting a sense from the top ranked words in each topic what these topics are about. Again, there's no supervision there. The only input from the user is the number of topics that you want. Similarly, the W factor gives you these document membership weights that allow you to rank the most relevant documents for each of the topics. Again, you've got a matrix where you can rank the values. In this case, it's the values on each column. And what you might do then is, for a topic like this, you might look at you could inspect the full documents. You might, depending on the format of your text, you might look at a headline or a title or so on. In this case, I'm just looking at the first the first line of each document, and this corresponds to. So this corresponds to this topic number 2 here, which appears to be related to Trump and Clinton, and then the top ranked documents for that particular topic, as you can see, naturally relate to the presidential election. So this type of topic inspection process is the way you might interpret and try to understand the outputs of topic models. And there are various visualization approaches that you might apply as well to look at how the topics relate to one another. But in the simplest case, what you might do is look at the descriptors for the topics, focus in on one of the topics. So here we can start to look at the actual weights themselves for these words. So here, this particular topic, it has strong weights for album, music, band, and so on. Further down, it has lower weights for Bowie, guitar, so on. And then you might start to look at the top ranked documents that are most relevant to this particular topic. So, here clearly related to music and bands in some particular way. So this is the typical output of a topic model. To sort of talk about a slightly more advanced topic before I finish up, a key problem in topic modeling when you're talking about NMF or LDA is choosing the number of topics. And again, it's kind of like, if you're familiar with k-means, choosing the number of clusters k in k-means. It's a difficult problem. A common approach is that you measure and compare what's called the topic coherence of different models generated for different values of k. So you might try NMF for smaller values of k and increase that to larger values of k. Topic coherence, basically, it's an evaluation measure for topic modeling. And the idea is it tries to measure the extent to which the words in the topic descriptor appear to be related to one another according to some kind of background corpus. There's lots of different measures for this, but the basic idea is that the words in the topic descriptor should be related to one another in some way. So, first topic here, we might say it has high topic coherence because all of these words are related to some kind of maritime text content. Second one, all of these words appear to be related to agriculture. But the third one, we've got these words where if you look at pairs of words, farmer and naval, or maritime, maybe maritime nuclear, but dairy and nuclear, it's not clear why these words might be semantically related to one another. So we might say this is a low coherence topic. So what we want to do is apply these measures that reward topics that look like these two on the left and that don't give a high score for ones like the one on the right. So the typical parameter selection approach for NMF might be something like this. You have to initially suggest what you might say is a sensible range, a guess for the value of k in a range of k mean to k max. You calculate the mean coherence of the topics for each of those values of k, and then you select the k value that gives you the highest mean coherence. So you plot effectively something like this and try and find the point at which you get this maximum coherence. So here, for the sample data set that I included here, when you run this process, you see that there are 8 topics in the data. It's worth noting that for k is equal to 7, for k is equal to 9 or 10, you may get reasonably sensible results as well. And often what happens is that if you increase the number of topics, what you'll find is that some of your topics get split into subtopics and sub-areas as well. Before I finish up, I just kind of talk about a couple of issues or a couple of sort of practical items that I've found when applying topic modeling over the last few years. In terms of when you're pre-processing your data, and this applies not just for topic modeling, but for any text mining approaches, stock word filtering often has a major impact on the results. It's a very manual process, it's quite subjective, but you'd be surprised, if you add certain words that based on domain expertise are not relevant, this can change your model considerably. TF-IDF, when you apply it with NMF, tends to work very well, it gives you better results. I mentioned this problem of random initialization earlier. This is a problem for both NMF and LDA, but there's a lot of research out there from people who just completely ignore this problem. They just run NMF or LDA once, and then they take the results as being definitive, and that's not necessarily the case. In terms of scalability, NMF tends to scale better than LDA, but the running times can increase considerably with NMF as your number of topics increases. So, you might be able to run it on your laptop for 100,000 documents for k is equal to 20, but if you start to increase it to k is equal to 200, you're going to be waiting a while for those results. Just in relation to the graph I showed on the previous page, like I said, there are potentially several good values of k. People tend to be a little bit obsessed about trying to find the exact correct number of topics. In fact, there might be several different topic models that can produce on the same data that tell you different interesting things. And again, the choice of sort of measure that you use to choose k could give you different results as well. Because of course this is an unsupervised process,